Hello students, and welcome to Lecture 6. This lecture is divided into two parts. Both parts are about the bones and the skeletons. So for the first time, this course will sort of feel like a real anatomy course because you always feel like you're studying anatomy when you're learning the names of bones in the skeleton. So this is our first official sort of feeling like an anatomy course. And in the first lecture on bones, I'm going to discuss the properties of bones in general. And then in the second lecture, Lecture 6, Part 2, we're going to learn the names of specific bones, the important bones in the human skeleton. Okay, so let's get started and just learn about the general properties and the general morphology of bones. So in this lecture, I'm going to talk about cartilage to begin with. So we mentioned the fact earlier that cartilage is a connective tissue, so is bone. And cartilage is flexible, but it's not as strong as bone. Bone is strong but inflexible. Cartilage is somewhat strong but flexible. So if you bend cartilage, it will bend rather than break. If you bend bone, it takes much more pressure, but it will eventually break. It generally doesn't bend. Now, the interesting thing, the reason why I mentioned cartilage and bone together is because bone is made from cartilage. So when we are developing, when a baby is developing in its mother's womb, initially the skeleton is made of cartilage, and then the cartilage undergoes something called ossification or mineralization, where the cartilage gets reinforced with various calcium salts, and the calcium and phosphate salts as well. And so the calcium in particular gives the cartilage more strength, and so we call it bone. Right. So there is some cartilage that's meant to be cartilage and it always remains cartilage, and there is some cartilage that's created with the intention of turning it into bone, right? So cells that create cartilage are called chondrocytes, and cells that create bone are called osteocytes. And because we're constantly building bone and taking bone apart to get at the calcium that we put into it, there are two types of osteocytes, osteoblasts and osteoclasts. Their job is to either build bone or to dismantle bone. Okay, and then we're going to learn about some of the ways that anatomists classify the bones. There are 5 general classes of bones, and then we're going to look at the microscopic anatomy of bones. You might know that bones, if you saw a long bone in half and then look at the cut edge with a microscope, you'll see that the bone tissue is organized into a series of concentric rings. The word concentric means within, right? So a series of concentric rings means a ring within a ring within a ring, and so on. And if you look at some bone tissue, it is made of a series of concentric rings. So those concentric rings are referred to as osteons, versus other types of bone that if you break it open, it looks kind of like a sponge on the inside. And we call that trabecular bone. And the sponge structures are referred to as trabeculae. All right, now then we'll talk about different hormones that cause bone to be created versus dismantled. We'll talk about the various things that you need to eat in your diet to have healthy bones. We'll also discuss some bone pathologies. We'll discuss the process of bone remodeling. Bone remodeling is a fancy term meaning to either build bone by taking calcium out of the blood and then putting it into the bone to make more of it, versus taking it apart in order, basically dissolving the bone and taking it apart in order to release the calcium in the blood. So many of the chemical reactions that take place in the body require calcium. Many of the enzymes use calcium as a cofactor, as a prosthetic group. And as a result of that, we always need to have a certain level of calcium in our blood. Do you remember what term we use to apply to something that's regulated that way? Homeostatic, right? So the blood calcium level is regulated homeostatically, And typically, if the blood calcium level drops to be too low, then your body will take apart some of your bone in order to release calcium into the blood. And the opposite, if the amount of calcium in your blood is too high, your body will put calcium into the bone in order to remove it from the blood, removing it from the blood and lowering the blood calcium level to the normal range. That is referred to as bone remodeling, the constant day-to-day building up and taking apart and dismantling of bone tissue. Okay, now as it happens at a certain age, when we're at a certain age in a certain period in our life, we're at a period where our bones are as dense and as strong as they can possibly be. That's referred to as peak bone mass. Right? Generally, peak bone mass is you reach peak bone mass approximately 5 years after you stop growing vertically. Right? So when you're growing vertically, you're not yet at peak bone mass, and then eventually you stop growing vertically, you don't get any taller. And then 5 years after that age is when you have the strongest bones you'll ever have. And then typically after that, you lose about 1 or 2% of your bone tissue every year until you're in your 70s or 80s. And if you have lost more than 50% of your peak bone mass, then they say that you have osteoporosis. Osteoporosis. So osteo refers to bones, and then porosis just means that you have more empty spaces in your bones. You have more pores in your bones because the bones have lost mass. Okay, and then we're going to get into some bone terminology. The way anatomists describe certain features of bones. You've seen bones, you know that some of them have rounded, bulgy parts, and some of them have flat spots and rough spots. All of those spots have a name. All of those different structures have a name, so we'll have to learn those. And then at the end, we're going to learn some bone pathologies. In particular, we're going to learn how to classify bone fractures. Bone fracture is the technical term for a broken bone, right? So the medical people never talk about breaking a bone. They always talk about a bone fracture. So the way bones break is not always the same. They break in various different ways, and so those fractures are classified differently. So we will learn how to classify bone fractures. All right, so the root word for bone is osteo. It's a Greek word, osteo, meaning bone. Right? And so you sometimes refer to osseous tissue, refers to bone tissue. An osteocyte is a cell that builds bone. An osteocyte is a bone cell, but typically a bone cell can be doing one of three things. It can be just sitting there, in which case you just call it an osteocyte. But if it's actively building bone tissue, you call it an osteoblast. Right? So you remember in a previous lecture we referred to a type of cell that builds connective tissue. It builds a cell that builds scar tissue, for instance, when we talked about skin regeneration. A cell that builds scar tissue by producing elastin, collagen, and fibronectin is called a fibroblast. So the word blast means a cell that's creating stuff. Right? So an osteoblast is a bone cell that's actively creating bone, building bone, and clast means to take apart or to tear down. If you have trouble remembering that word, I always remember the word iconoclast. An iconoclast is somebody who specializes, usually somebody like a comedian or somebody who specializes in belittling authority figures, belittling or making fun of authority figures. You call that because an authority figure is an icon. And if your job is to belittle the icons, then you're an iconoclast. And so the word clast means to take apart. So osteoclast is a bone cell who is actively taking the bones apart. Right, so we have three types of bone cells. All three of these are called osteocytes. But if those osteocytes are doing nothing, you just call it an osteocyte. If they're building bone, you call it an osteoblast. If they're taking bone apart, you call it an osteoclast. Okay, now what is the function of bone? Obviously, it supports the body. It protects some of the organs. Now, here's an interesting thing for you. What is the difference between an exoskeleton and an endoskeleton? right? So just as a little aside, a little historical aside, you know that some organisms on Earth have their skeleton on the outside, arthropods, for instance. So if you look at crustaceans like lobsters and crabs, they have this tough skeleton that's on the outside of the body. So you can hit a crab or a lobster with rocks and other things, and they won't be damaged because they have this hard shell on the outside, but they don't have a skeleton on the inside. So once you take your crab and you boil it or something and you break it open to eat it, you don't have to worry about finding any other bones on the inside because it doesn't have any. It has an exoskeleton. The word exo means a skeleton on the outside. Humans have an endoskeleton, meaning they have a skeleton on the inside. Now, some of you that are interested in philosophy and theology and things like that might want to ponder this question. If there is a God who created, there is a branch of Christianity, for instance, that's called intelligent design, and intelligent design says that the human body is so complicated, it is so complex, and it does all of these amazing things. It couldn't possibly have happened by chance. Somebody must have designed the human body. There must be a creator who designed the human body to be where it is. And a lot of atheists, I'm not one of them, but a lot of atheists say, well, if you were God and you had the intelligence of God, why would you build the human body that way? And one of the arguments that they raise is they would say, well, why on earth would you put a protective shell on the inside, right? That's like taking a bunch of soldiers and instead of putting them into the tank, you put them on the outside of the tank, and the inside of the tank is empty, right? So as soon as a bullet goes by, you kill the soldiers because they're not inside the tank. That makes no sense, right? So I happen to believe in God. I'm a religious spiritual person, but I happen to be one of those people who think that God created humans. Humans are the ultimate creation of God, but the creation is not finished yet, and that the creation is taking place through the process of evolution. So there are many people who are religious and spiritual who believe in evolution, and I'm one of those people. You'll find other people in Columbia College and all over the world some of them are atheists, and some of them are religious, and some of them believe in creationism. Creationism is the idea that, intelligent design. And intelligent design is the belief that the mere complexity of the human body, the way it works so well, all of these parts working very well, the mere complexity and complicatedness, the human body is such an amazing machine that it in and of itself must be proof of a divine creator. And then people like me will say, well, I'm not disputing the existence of a creator, but I don't think the creator would have designed anything this way. I mean, why would the creator design humans with an endoskeleton where you hit a human with a rock, they get a bruise, maybe a hematoma, maybe they die because the skeleton isn't really protecting very much. If you put all of the soft tissues, you put all of the soft parts of the body outside the skeleton, that makes absolutely no sense. There are other things that make absolutely no sense, like the fact that why would you design, if you were an intelligent creator, why would you design the human body to have a lifespan of 100 years, and yet your knees typically start to wear out when you're 40 or something like that? So what's the point of that? Why would you design the human body so that wisdom teeth come in when you're in your 20s or 30s, and they cause all kinds of problems with your teeth? Why would you do that? If you were designing the human body, there are a lot of things that you would probably design differently, but I don't think the human body was designed. I think it evolved. But that does not exclude the presence of a creator. I just don't happen to think that the divine creator is involved in this kind of thing. So humans have an endoskeleton. Many organisms on Earth have an exoskeleton. Okay, because the human body has an endoskeleton, it provides protection for organs, but only some organs. So, for instance, the heart and the lungs are protected to a certain extent by the rib cage. which we'll talk about later. But a lot of the organs in the abdomen are not protected at all. So if you hit somebody, around the umbilical area, you could damage their kidneys or their intestines, and there are no bones there to protect them at all. That's the same for humans and all the mammals. Okay, so the functions of the skeleton are support movements. The fact that the muscles are attached to the bones allows us to move. The fact that the muscles are moving around this rigid, strong skeleton allows us to move quite easily. That's a good thing about the design. Um, it it provides some limited protection of the organs. I guess the other obvious example of protection is the brain. So the skeleton does a very good job of protecting the brain, not such a good job of protecting the kidneys or the intestines. Okay, so movement. You attach the muscles to the skeleton through a lever system, what's known as a lever system, and you can move around. Another function of the bones, which is very important, is known as hematopoiesis. Hematopoiesis, you need to memorize this word. Hematopoiesis means the creation of red and white blood cells within a certain type of bone marrow called red bone marrow. Now, if any of you have seen a bone break, I know many of you are vegetarians, but if some of you eat meat, you might have, or chicken or anything like that, you might have seen that when you break a bone open, there's kind of a sticky, gooey substance on the inside. Uh, if you break open one of the long bones, like the long bone in the leg or the long bone in the arm, the long bone in the leg is called the femur, the one in the arm is called the humerus. You know that by now from the handout. Right, so if you break open a humerus or a femur, there's a yellow sticky substance inside. That is nothing but adipose tissue. That's fat cells. Right, so that's one of the reasons why dogs love to eat those bones. They have these nice sharp teeth and strong teeth, and they crunch open the bone, and they don't eat the bone. They lick the marrow out from the inside of the bone. Okay, so the long bones, the humerus and the femur, they contain fat, storage fat. But the ribs and the pelvis and the pelvic bones and the skull bones, if you break them open, they are red on the inside. Now, the reason they're red on the inside is because that's where red blood cells are being created. Right? So we call that type of bone marrow red bone marrow. And so the red bone marrow, specifically the ribs, the skull, the pelvis, and the spinal cord, these are the areas where bone marrow cells are being created, where blood cells are being created. And we call that process hematopoiesis. Hematopoiesis. Okay, now let's talk about the way different types of bone are classified. Some forms of bone are more dense and solid and strong than others. Okay, so as I mentioned, bone starts out in humans and other mammals as cartilage. And the cartilage is reinforced with calcium salts, which make it eventually turn it into bone. That process is referred to as ossification. Right? The conversion of cartilage into bone is called ossification. Now, here's an interesting side story. Again, I'm not going to ask you about evolution or creationism or intelligent design in this class. Those are subjects for religious classes and philosophy classes. But the interesting thing about evolution is that on the evolutionary time scale, the first animals in the world were fish in the ocean. And the earliest fish had cartilage skeletons. They had skeletons that were made of cartilage, and we call those chondrichthyans. And then later on, some of the chondrichthyans evolved into what are called osteichthyan fish or bony fish, where they put mineral salts into the bones to create bony fish. Right, so ossification, so it's kind of like when humans and other animals are developing in their mother's womb, they kind of go through a little miniature evolution where they start out with a cartilage skeleton, and then that cartilage skeleton ossifies to become a bony skeleton. Right, so as I said, sharks, for instance, are a good example of chondrichthyans. Those are the fish that have a cartilage skeleton. You'll notice that it's very rare to find the skeleton of a shark because cartilage dissolves and decomposes faster than bone. But then eventually some of the chondrichthyans evolved into osteichthyans, which are the bony fish, as you see below. Now, when you look at bones, there are two types. One type is called spongy bone. The technical term is trabecular bone versus compact bone. Trabecular bone tends to form the red bone marrow, and compact bone is used mainly for strength and is not used for hematopoiesis. Okay, then furthermore, if you look at all the bones in the human skeleton, if you look at just kind of the central shaft of the human skeleton is referred to as the axial skeleton. That includes the skull, the spinal cord, the ribs, and the pelvis. And then the appendicular skeleton, remember that an appendage is something that you stick on to the end as an afterthought. Right, so you have these at the end of a book, you have an appendage, means that you just stick it on as an afterthought. So the appendicular skeleton refers to things that you have stuck on to the axial skeleton, things that you have attached to the axial skeleton. Right, so that includes the arms and the legs, basically. The arms and the legs are what we classify as the appendicular skeleton, whereas the skull, the spinal cord, the pelvis, and the ribs are the axial skeleton. So here you see the axial skeleton labeled in blue, and then the appendicular skeleton is just labeled in white. Now, as I said, the spongy bone, the trabecular bone, is where blood cells are created. So this is the head of the femur. This is the bone in the leg down here, right? And if you break open the head of the femur, you'll see that it's composed of trabecular bone, and it's usually red. This bone has been dead for a while, but if it was freshly broken, you would see red on the inside because red blood cells, as well as white blood cells, are being created there. All right, as we said, bone remodeling is where you build bone up or you take it apart depending on how much calcium your blood needs. So an osteocyte is a bone cell. They live inside little holes in the bone referred to as a lacuna, lacunae plural. Right? An osteoblast is an osteoclast that builds bone. An osteoblast is an osteocyte that builds bone. And an osteoclast is an osteocyte that takes bone apart in order to release the calcium into the bloodstream. All right, there are 5 general classifications of bones. You do need to know these, and you do need to know at least one example of each of these types of bones. Long bones are longer than they are wide, example the femur. Short bones are roughly the same length as they are width, example the carpals. Where are the carpals again? Do you remember? The carpals are the bones of the wrist, right? Flat bones are, as the name implies, flat. They're flat and thin. So the sternum and the cranial bones, the sternum is commonly called the breastbone. The cranial bones are the bones that protect the skull. Those are good examples of flat bones. Then we have a few bones in the body that are classified as irregular bones, meaning that they have all sorts of bits and pieces that are sticking off here and there, and it looks very irregular. And the best example of these bones are the vertebra. The vertebra are the bones that make up the spine, the spinal column. And then finally, there are some bones that are classified as sesamoid bones. The word sesamoid refers to a sesame seed. Right? So if you've ever eaten sesame seeds, you know what a sesame seed looks like. And so a sesamoid bone is a bone that is the same shape as a sesame seed. The only example really that we ever use is the patella. Do you remember where the patella is found? The patellae, or patella, singular, is the kneecap, commonly called the kneecap. That bone is referred to as the patella. So a long bone, example the femur, which is the bone in the upper part of the leg. There's the part we were just looking at that was broken open. And so there is, in fact, the head of the femur, this part of the femur is made of trabecular bone, spongy bone, and the shaft is made of compact bone, which is the stronger of the two types. All right, short bones, example, the carpals or the tarsals. This picture here is the tarsals. So these are the bones in the ankle, They fulfill the same purpose as, the ankle versus the wrist. In the wrist, you have a bunch of these little short bones that are roughly square in shape, and those are called the carpals. And then here in the ankle, we have a bunch of little tiny bones that are roughly square in shape, and those are the tarsals. Okay, this is the breastbone, commonly known as the breastbone. The correct term is the sternum. It is a flat bone, just as the bones in the skull, the cranium, are flat bones as well. Okay, so here's the skull bone. If you look at a flat bone, it has trabecular bone inside. So it has this spongy appearance on the inside. So the flat bones are most always trabecular bones. Right? Whereas the long bones usually have the long shaft of a long bone is usually a compact bone. Irregular bones like the vertebra, right? So here we have all these things that are sticking off. This is called a process. Actually, all three of these things are processes. A process is a piece of a bone that sticks out, kind of a pointy bit that sticks out. This hole in here, the vertebral foramen, is where the nerves from the brain go. So the spinal column is actually running through that little hole. And the patella is the only sesamoid bone that we need to learn. Difference between spongy versus compact bone. So bone is organized into ring structures that are made of lamellae. Lamellae are a fancy term meaning layers, right? Layers or rings of tissue. Okay, now the spongy bone is where the red blood cells and white blood cells are being created through a process called hematopoiesis. And spongy bone is organized into a kind of a loose network that looks like a sponge. And the networks are called trabeculae. Right, so all of these little spongy structures individually are called trabecula. Plurally, they're called trabeculae. Versus compact bone, which has more strength, which is made of rings of lamellae that are rings within rings within rings. And so rings within rings, those are referred to as concentric circles. Concentric circles are concentric rings where you have circles within circles. And running down the center of these layers within layers, you have a hollow space that's referred to as a Haversian canal. We'll talk to that later. And these rings within rings with the hole down the middle are referred to as osteons. Osteons. So this is an osteon. We're looking downwards on it, right? So somebody has taken a saw and cut this bone in half along the transverse. They've made a transverse section through the bone, and now we're looking down the shaft of one of the long bones, and you can see these rings within rings, and then with a canal in the middle. That's referred to as an osteon. That's called an osteon. Okay, so here is the head of the femur. And so we have trabecular bone in the head. So in the shaft of the femur, the long part, we have compact bone. It's actually hollow in the middle, but the sides are made of compact bone. You can see it written there. Right. And then inside the head of the femur, we have trabecular bone that is red in color because it's producing blood cells. Same thing for the skull, trabecular bone. If you look at the trabeculae up close, they look like this. They are lamella. They are formed of rings of lamella, but not as big. The rings are not as big as you find in compact bone, and there's no canal down the center. All right, here we have compact bone. So you can see that this section is taken from the side of the shaft of the humerus, rather. And you see here we have an osteon, which is rings of lamella, concentric rings within rings. And then down the center, you can see it better in this one here. Down the center, we have a canal, which is referred to as a Haversian canal, a Haversian canal. Now, that canal contains blood vessels and nerves, right? So that's why it hurts when you break a bone. You would think, if there were no nerves that ran through bones, it wouldn't hurt when you break a bone. but because when you break a bone, those nerves get pinched, they get compressed, and that's why it hurts so badly when you break a bone. So the Haversian canal is a place where blood vessels and nerves can actually run through the bone. And then the Haversian canal runs parallel to the lamellae, right? So it's running in the same direction. Now notice that we've got some blood vessels who are coming this way. In fact, what those blood vessels are doing is they're coming from the outside of the bone and connecting with the Haversian canal. And those blood vessels are running through a canal that's perpendicular to the lamellae, and a canal that's perpendicular to the Haversian canal, and we call that a Volkmann's canal. And I'll show you how to spell those things next. So there's an osteon, typical osteon, with a Haversian canal running down the center, and that Haversian canal contains veins, arteries, and nerves. By the way, in anatomy diagrams, in anatomy books, veins are always drawn in blue, arteries are always drawn in red, and nerves are always drawn in yellow. Right, so if you're looking through the OpenStax anatomy book, you see the colorized color chart. If you see blue things, those are supposed to be veins. If you see red things, those are supposed to be arteries. If you see yellow things, if you see little yellow strings, those are meant to be the nerves. Okay, so in Osteon, this particular bone structure was discovered by an anatomist named Havers, and so the Osteon is named, sometimes called a Haversian system, and that's why you have the concentric rings of bone called lamellae. That means layers, and then the canal down the center that runs parallel to the lamella is called a Haversian canal. Right, the Haversian canal contains blood vessels, nerves, and lymphatic vessels, which we haven't discussed yet. But lymphatic vessels contain another type of fluid called lymph. Right. So, by the way, lymphatic vessels are also drawn on anatomy charts as being colored in yellow usually. So, sometimes on some anatomy books they draw the lymphatic vessels in green, which makes it harder to confuse them with nerves, but you'll see examples of each. Anyway, so the blood the blood vessels and the nerves and the lymphatic vessels have to get into the Haversian canal. So you have these perpendicular canals that run into the bone, and they are referred to as either perforating canals. Perforate means to puncture, or to puncture or to drill into, right? And then they can also be known as Volkmann's canals, which are named after somebody else. So we have the Haversian canal going parallel to the rings, and then we have the Volkmann's canal running perpendicular to the rings. And then inside the bone we have osteocytes that are trapped within lacunae. Right, so there's the Haversian canal. Right, so we're looking down the Haversian canal. Okay, there it is again. Okay, now when we are a developing embryo, so when a child or a human or an animal or any mammal is conceived, you have an egg and a sperm. When the sperm and the egg get together, you have a structure called a zygote. We'll talk about all this later. And then the zygote turns into something called a blastula, and then something called a gastrula, and then something called an embryo, and then a fetus, and then a neonate. Right? So the neonate is a newborn baby. All right. Now an embryo is an early rudimentary baby, in other words, right? So a developing embryo. In the embryo, the skeleton is originally made of fibrous membranes and also a type of cartilage called hyaline cartilage. Hyaline is a Latin word meaning fogged glass. Foggy glass. So in a bathroom you have a window that's foggy so people can't see in. So that would be an example of hyaline glass. And so hyaline cartilage, it has the appearance of glass. It has the appearance of kind of that translucent but not transparent whitish glass, right? And so the bone in the developing embryo is originally made out of hyaline cartilage, which is produced by chondroblasts. The hyaline cartilage is made of the same stuff that other forms of cartilage are made of, which includes hyaluronic acid, chondroitin sulfate, and collagen fibers. All of those things are produced by chondroblasts. Okay, so ossification is where you convert the cartilage into bone by uh, saturating it with mineral salts, including calcium phosphate and calcium carbonate. Collectively, calcium phosphate and calcium carbonate together are collectively called hydroxyapatite. Hydroxylapatite. Right, so hydroxylapatite refers to the various calcium salts that are put into cartilage in order to convert it to bone during the process of ossification. All right, so you notice that when you grow, sometimes the bones get longer along the long axis, and then as you get older, they tend to get thicker as well sometimes until you reach peak bone mass, and then they don't get thicker or taller anymore. And then sometimes you build up and take apart these bones in order to put calcium into the blood or take calcium out of the blood. Okay, so obviously one of the most important things that you need to eat in order to have healthy bone development is calcium. You can take calcium phosphate and calcium citrate and calcium carbonate pills, and you can take those as dietary supplements, and you should, because you can never have too much calcium. There are other things you can have too much of, but you can never really have too much calcium. But another place that you can get calcium is in dairy products, of course. So milk and cheese are enriched with calcium. They tend to have lots of calcium. Other than that, there are a few other places you can get calcium, but dairy products are the best. Right? And we already discussed the fact that our body creates a precursor, an inactive precursor to vitamin D, and sunlight in our making contact with our skin is what converts that into active vitamin D, and then we need active vitamin D in order to absorb the calcium into our bones. There's another thing that helps us absorb the vitamin D helps us absorb calcium in our intestine. So that's how we get the calcium from our food. You know, when we're drinking our milk and eating our yogurt and eating our cheese, in order to get the calcium from those foods into our bloodstream, we need vitamin D, and that is created by sunlight. If you're in an area where you don't get enough sunlight, you should take vitamin D supplements, right? And then, in order for the calcium to get from the bloodstream into the bone, we need vitamin K. So vitamin K is critical for that. And humans produce their own vitamin K, but do you remember where we get the rest of it? We get the majority of our vitamin K from friendly symbiotic E. coli, Escherichia coli bacteria that live in our colon. So that's an example of why E. coli, Escherichia coli, and humans have a perfect symbiotic relationship. As well, animals have E. coli in their intestine as well. All the other animals do. And it's a symbiotic relationship because we each benefit from the relationship. We get the we get the vitamin K that they provide, and they make a lot of it, excess amounts. And so we benefit by getting the vitamin K that they produce because they produce so much of it, and they benefit because they get a nice, warm, protected place to live where there's an abundance of food that's going through our digestive system. So the relationship between humans and other animals and Escherichia coli bacteria that are in the large intestine is a perfect example of a symbiotic relationship, what biologists call a symbiotic relationship. Now, you've probably also heard that you need to have omega-3 fatty acids, and the reason for that is because the omega-3 fatty acids, among other things, they help the osteoblasts to work. You get omega-3 fatty acids mainly in oils. You can get them in vegetable oils. You've probably seen people selling fish oil tablets. If you eat lots of fish, then you don't have to take those tablets because you know that fish are fairly oily to begin with. And so you get a lot of omega-3 fatty acids if you eat fish or if you take fish oil supplements, cod liver oil, for instance, salmon oil, and so on. All right, now bones are the signal for the body to build bones or to take bones apart is controlled by hormones. Hormones are signals. They're not radio signals or television signals. They are basically protein signals or lipid signals that are produced by endocrine glands. And over here on the right side of the screen, I've listed some of the endocrine glands, including the pituitary gland, the thyroid gland, the parathyroid gland, and so on. So hormones are signals that are made of either proteins or lipids, and they are produced by endocrine glands, which are part of the endocrine system. And they are sent out into the body, and they go out and they tell cells and organs and other parts of the body to do things. They're kind of like a control center, like telegrams. And so the building of bone and the taking apart of bone, collectively called bone remodeling, is controlled by some hormones, some specific hormones, which you do need to memorize. All right. So growth hormone, abbreviated GH, is produced by the pituitary gland of the brain, right? And it stimulates proliferation of the chondrocytes in a structure called the epiphyseal plate. Right? So the epiphyseal plate is the bulgy part it's kind of in the middle of the bulgy part of what you've seen a long bone. There's a central shaft, and then there's a bulgy part at the top and the bottom. About halfway through the bulgy part at the top, you have a structure of dense connective tissue, dense cartilage, that's referred to as the epiphyseal plate. And the chondrocytes inside that cartilage are busy creating new bone. And they're doing this they're doing this at the behest of the growth hormone. Right? So growth hormone is produced by the pituitary gland, and it causes the chondrocytes in the epiphyseal plate to cause the bones to elongate and become longer. Okay, so making the bones long, that's when we're growing up. When we're children, we get taller and taller. That is due to the effect of the growth hormone, causing the chondrocytes in the epiphyseal plate to elongate the bone, to make them longer. Right. Okay, now once we're fully grown, how do we control putting calcium into the bones and taking it out? We're not going to get any taller, so growth hormone is of limited use to that. But there are two hormones that tell our bones to put calcium in or take calcium out. Okay, so there is one hormone called calcitonin that's produced by an endocrine gland called the thyroid gland, which tells the calcium to go into the bone. And I suggest the way you memorize that is that calcitonin has the word "in" inside it. Calcitonin. So the calcium goes in the bone thanks to the calcitonin. Okay, the other hormone that controls bone density and bone mass is called parathyroid hormone. Parathyroid hormone causes calcium to come out of the bone, right? And parathyroid hormone is produced by a gland called the parathyroid glands. There's 4 of them, and we'll talk about them later. Okay, so we have 3 hormones that control the behavior of bones. We have growth hormone, which causes bones to elongate and become longer because that growth hormone stimulates the chondrocytes inside the epiphyseal plate when we're growing vertically. And then whether we're growing vertically or not, there is calcitonin and parathyroid hormone, 2 hormones that control whether calcium goes into the bone or comes out. What is peak bone mass? Peak bone mass is where you have the maximum bone density, and generally you have peak bone mass about 5 years after you stop growing vertically. I stopped growing vertically when I was about 15 years old. So when I was 15 years old, I'm the same height that I am now, which means that I had peak bone mass at about age 20. You had peak bone mass about approximately 5 years after you stopped growing vertically. And then once you hit peak bone mass, you start to lose, we don't know exactly why, but you start to lose about 1% of your bone mass every year. So you can see that, by the time you're 40, if I hit peak bone mass when I was 20, then by the time I'm 40, I've lost 20% of my bone matrix, the density of bones. So my bones were weaker at age 40 than they were at age 20, and then I'm nearly 60 now, so they're weaker still. And this trend continues. So when somebody's 80, they've lost more than 50% of their bone mass, and they have osteoporosis, which means the bones are very easy to break. Right? So osteoporosis is that condition where you have less than 50% of your peak bone mass, and it's very easy for your bones to break. Another thing we need to be aware of is the fact that for women, the bone mass loss is quicker than it is for men, and this is due to the balance of hormones that take place in a woman's body versus a man's body. So you will find more elderly women that have osteoporosis than elderly men who have osteoporosis. Generally, anybody who's over 65 or so has brittle bones, but some people's bones are extremely brittle. For example, this is very tragic, but it's not uncommon. This happens every day that occasionally somebody will literally break the bones in the hand of an elderly woman by shaking her hand too firmly. So with elderly women, we have to be very careful about protecting them from injury, because their bones are very easily broken. And for an elderly man, they're easily broken as well. So elderly men have to be careful too, but elderly women especially. All right, so this graph here shows peak bone mass. So for men and women, about 5 years after you stop growing vertically, you end up at peak bone mass, and then the density of your bones begins to decline. So in men, you can see here that they lose and lose and lose. Then when you're in your 80s or so, you've lost 40-50% of your bone mass. Now look here. So women, peak bone mass, and then here, approximately around age 45 to 55, there's a dramatic loss in bone marrow, not bone marrow, but bone mass, bone density, because of the balance of hormones, the rebalancing of hormones that are produced during menopause. Menopause is the age when a woman stops producing eggs and stops menstruating. So there's generally, when you stop menstruating, your bones also start to become very brittle. So middle-aged women should make sure that they have, just in order to slow this process down, middle-aged women, you can't avoid it. You can't avoid having brittle bones during menopause, but you can kind of lessen the severity of it if you make sure that you have lots of calcium when you're in your 40s and on for the rest of your life. Make sure, take calcium supplements, take lots of it, eat lots of cheese and dairy products, but certainly you can take calcium pills. And there are various drugs that you can take that your doctor will recommend that help the calcium to be absorbed into the bone more easily. And just do everything you can to avoid losing more bone mass than you absolutely have to, because it's very difficult to get it back once it's been lost. Okay, so bone loss due to menopause. There's this drastic period here between ages of about 45 to 55, where there's a rapid increase of bone mass in women that men don't actually suffer from. Okay, so here on the left, we have a regular bone matrix, and on the right, we have osteoporosis. Notice how porous the bone matrix is on the right. It's porous, it has less density, and it's more easily broken. Right, so that is why it's easier for elderly people to fracture their bones, because the bones are not as strong. And that's exactly why we always give our seat to the elderly person on the bus, because they have special seats at the front of the bus that are reserved for the elderly people, so that they get on the bus, they don't have to try and walk all the way to the back of the bus while the bus is moving, because they might fall onto the floor. And if an elderly person falls onto if a young person, I'm not so young anymore, you maybe, so if you fall on the floor, you get a bruise, and 2 days later you're fine. You have a painful bruise for a day or so, and then you're fine. If somebody who's 70 or 80 falls on the floor, they might break their hip, and because their bone isn't being created very quickly at that age, it may never heal properly. In fact, it usually doesn't. So if you're young, you have strong bones, you fall on the floor, the odds are that you don't break any bones. But even if you do break bones, they'll heal perfectly. They'll heal back up again, and they'll be pretty much as strong as they ever were. If an elderly person breaks a bone, they will break a bone much more easily, and it may never heal again. It will never be the same again. So as you know, getting old is not a matter of gradual degrees. Generally, when you get old and infirm, you see somebody who's old and infirm, they have to walk with a cane or something like that. The odds are that they started walking with that cane after they broke a bone. And so if you can avoid breaking bones, then you can avoid walking with a cane. Right? So that's why society as a whole should do everything that we can to avoid having elderly people get broken bones. So we need to design buildings around ergonomically sound building designs to make sure that it's not, the stairs shouldn't be too steep so that people fall down and break bones and other things. There are other things you can do. That's why we have the courtesy seats at the front of the bus to avoid elderly people breaking bones, and all of these things. If we can design our society in such a way that it's less likely that elderly people will break bones, then people will not be as infirm in their old age. They'll have fewer health problems and so on. So these are all things that we have to consider. I know that some of you are not studying biology. Some of you are taking this course as an elective, but some of you that are taking this course as an elective, you're studying economics and you're studying public policy and sociology and anthropology. You will someday, perhaps, I hope, be in a position where you can influence these kind of policies, right? So you should be aware of the consequences of public policies, and so this is one of them. All right, let's go back to more trivial technical things and learn about the gross anatomy of bones and the specific words that we use to describe the various parts of bones. All right, so at the proximal and distal end, right? You remember from the early lectures what the difference between proximal and distal is. At the proximal and distal end of every long bone, you have a structure called an epiphysis. Right? The epiphysis is the bulgy part at both ends of a long bone, and it is usually covered with cartilage that's referred to as articular cartilage. And the bone the epiphysis is made of spongy bone. Right? Now, articular cartilage, what does the word articular mean again? Right? The word articular refers to joints. So, any bones that participate in joints, particularly the bones of the arms and the legs that participate in joints, the epiphysis, where the joint is, right? So, if you look at the humerus, there's a bulgy part at the bottom and a bulgy part at the top. The bulgy parts are the two parts that are participating in the joint. And those epiphyses are coated on the outside with a kind of looks like a plastic called articular cartilage. Right, so the epiphysis, the distal and the proximal epiphysis of the long bones are made of spongy bone and covered with articular cartilage. The long part of a long bone is called the diaphysis, right? And so the long part between the two epiphyses is called the diaphysis, and it is hollow on the inside. And the hollow part on the inside is called the medullary cavity. The medullary cavity. Generally, the outside of an organ or a structure is referred to as the cortex, and the inner part of an organ or a structure is called the medulla. So that's why the inner part of this long bone is referred to as the medullary cavity or the medulla. And in a long bone, the medullary cavity is filled with yellow bone marrow, which is just adipose tissue. It's just fat cells, fat storage cells. Now, all bones are lined on the outside and lined on the inside with membranes. We discussed membranes when we discussed tissues. Right, so there is a membrane lining the medullary cavity of a long bone, and it's called the endosteum. Right? Remember, of course, that endo means inside. Now, you also know that exo means outside, and so if you were being logical about naming these things, you would call the outer membrane of a bone, the membrane that surrounds the outside of the bone, you would call that an exosteum, but they didn't. for whatever reason, they decided to use the other word, the word periosteum. So osteum means bone, and the word peri means on the outside, around the outside, or around the perimeter. Perimeter means like out at the outer edges, right? So for all bones, we have two membranes. One membrane is on the inside, one membrane is on the outside. The membrane on the inside is called the endosteum. The membrane on the outside is called the periosteum. And on a long bone, there's a big hole in the middle that allows the blood vessels to get into the long bone, and it is referred to as a nutrient foramen. You're going to learn in a few minutes that the word foramen is a Roman word meaning hole. It just means a big hole. So nutrient foramen is a big hole in the diaphysis of a long bone that allows the blood vessels and the lymphatic vessels and the nerves to get in. Okay, I mentioned already that within the epiphysis, there's a little line of very dense connective tissue that's referred to as the epiphyseal plate, and that's where the bones grow vertically. That epiphyseal plate is made of hyaline cartilage, and it contains chondrocytes. Those are the cells, the chondroblasts, the cells that build the cartilage, and that is where the bones grow vertically when we're growing taller as children. And then even as an adult, you can still see the remnants of the epiphyseal plate, which is referred to as the epiphyseal line. So here's our bone, right? Here, these bulgy parts at either end are referred to as the proximal epiphyseum, right? And the distal epiphysis, right? This one is down here by the knee. This is the femur, by the way. So here's the head of the femur by the pelvis, and here's the distal epiphysis near the knee, near the patella, right? And you can see on the inside that the epiphyses are filled with spongy bone, trabecular bone, and then it's hollow on the inside. That's the medullary cavity, and then there's the nutrient foramen bringing the blood vessels on the inside to feed the adipose cells that are living inside the medullary cavity. Right? And the edges of the shaft, the edges of the shaft are made of compact bone, right? So they're made of osteons. And then lining the inner medulla, we have the endosteum, and then lining the outside of the bone, we have the periosteum. And by the way, when the bones, the muscles are attached to the bones, the muscles don't attach directly to the bones. They're actually attached to the periosteum. So this sheath of tissue that surrounds the bone is actually what the muscle is attached to, not the bone itself. All right, let's learn some really interesting terms to describe every bump and groove and curve that you would find on a bone. Okay, so first of all, articulations refers to joints, right? And then we also have special names for holes, special names for smooth surfaces versus rough surfaces. We have special names for bumps. We have special names for grooves and hollow spots and long flat surfaces within bones. Okay, so the word foramen is a Latin word meaning hole. So for instance, at the base of the human skull, there's a great big hole that lets the nerves in and out of, it lets the long nerves in and out of the brain, in and out of the cranium, right? So the nerves come out of the brain and run down the spinal column through a big hole that's referred to as the foramen magnum. The word magnum means big, the word foramen means hole, so it literally translates as the big hole. Okay, a meatus is a small hole that leads to a canal. Right, so for example, there's a hole in the skull that the ear goes in through, which is called the auditory meatus. There's also, the word meatus also just can refer to the opening to a small tube or a small canal. So for example, later on when we talk about the renal system, the urinary system, in women, in both men and women, the urine comes out of the body through a tube called the urethra. In women, the urethra terminates, the urethra comes out through a small hole called the urinary meatus. So there's kind of like a little soft, puffy structure of tissue where the urine comes out. That's called the urinary meatus. So meatus means the opening to a small hole. So when we're talking, in this case, we're talking about a meatus in a bone. So there's several meati around the skull and other places where you have small holes. The most obvious one is the auditory meatus, in other words, the ear hole. Okay, a canal is a tunnel through something, so there are various canals. A fissure is a crack, right? There's a small, looks like a crack, except that it's meant to be there. Okay, a sinus is a hollow pocket, right? So you know that the skull is filled with sinuses. All right, now talking about surfaces, a facet is a flat polished surface. You probably know that a diamond has facets on it. So a facet is like one of several surfaces that are flat and nicely polished. Right? A condyle is a rounded surface on a bone, and a tuberosity is a rough surface on a bone. Generally, the muscles, I just mentioned that the muscles are attached to the periosteum, but usually they're attached to the periosteum at a rough spot on the bone called a tuberosity. So generally, when you see a piece of a bone that's kind of bulgy and rough, that's usually an attachment point for a muscle, and it's usually called a tuberosity. Okay, so you know what a facet of a diamond is. So a facet of a bone is a small, flat surface. Okay, now bumps. Okay, so a process is something, usually a pointy piece that sticks out from a bone, and it's usually somewhat sharp, right? So the spinal cord, you know that you have these sharp bones, these sharp little pointy things that are on the back of your spine facing the posterior side of your body, and those are the spinal processes. Right? So it's a bone process is a little pointy part that sticks out of the bone. Okay, a tubercle is a small rounded process, right? So if you have if you have something that's a piece that sticks out from a bone and it's long and sharp, you would call that a process. Whereas if it's small and rounded, you would call it a tubercle. So a crest is basically a ridge, right? So a long angular surface. And a ramus is a ridge or an edge as well, usually a flatter surface. All right, what about giving names to grooves and dents? Right, so a fossa is an elongated kind of a basin shape. So the best example of a fossa is inside the pelvis. You know how the pelvis kind of is nice and smoothly curved on the inside that looks like, it kind of looks like half of a bowl or a fragment of a bowl. So that's a good example of a fossa. A fovea is a small pit, right? So a very small dent. The head of the femur, for instance, has a little tiny hole punctured in it that's about the size of a pencil point, and that's called a fovea. You also have a fovea at the back of your retina and the back of your eye, this little thing that's called the fovea as well. Okay, now a sulcus is a groove, like a trench. Like so a dent, a long and elongated dent in the surface. If it's fairly narrow, like a trench, is called a sulcus. And then sometimes if you have a bump that's near a sulcus, you refer to that as a gyrus, but we'll talk more about that later. All right, so here, this is a spinal, this is one of the backbones. It's a spinal vertebra. And notice that we have two flat facets right here, and there's actually two more there. So those bits of the spinal vertebra are all classified as facets. So are those. Right. This big hole in the middle is classified as a foramen, right? And then this pointy thing that sticks out is classified as a process, right? So that's three of the terms that we learned. Okay, so here we have on the left, this is the femur and the leg from the leg, and on the right we have the humerus from the arm. Right, so notice that there's a rounded bit here, that's a tubercle. And then here's a rough piece that some muscles are attached to. There's a tuberosity. right? And then there's a little tiny fossa here, a rounded surface. And then here we have condyles, these rounded bits here, the condyles. Right? So fossa, condyle, tuberosity, and tubercle. All right, so here's a crest, right? The iliac crest. And then here's the iliac fossa, this kind of rounded bowl shape. And here we have a bunch of sinuses. Right, so you can see the sinuses in green, these hollow spots in the skull. Right, and then you have some cracks behind the eyes. These eye holes are called the orbits. And then you see some cracks there. And then there's some little holes. There's a foramina, some little foramina. And then there's some canals. All right, here's the jawbone is referred to as the mandible. And then there's a little bump that attaches the jawbone to it's a little hinge it's a bump basically that acts as a hinge to attach the jawbone to the skull. And it's called the mandibular condyle. And if you look at it, it's a rounded little bump that's acting as a hinge to hold the jawbone onto the skull. And then here we have the mandibular ramus, this flat surface that's in the mandible. Okay, here we have a very important hole called the foramen magnum, which is where this is looking at the bottom of this is an inferior view of the skull, so we're at the bottom looking upward through it. And there is the big hole that lets the nerves out of the skull down the spinal cord. So that's the foramen magnum. All right, let's quickly discuss some bone pathologies. Okay, so as we've heard before, the word pathos means to suffer, and the word logi means to study. So pathology is the study of things that make you sick, basically. The things that make you suffer. Pathology is a branch of medicine, which is the study of diseases. And a pathologist is usually a physician who has a medical degree who specializes in studying things that make you sick, rather than they may not remember. They learned a lot about how to cure things in medical school, but they've probably forgotten a lot of them. And so a pathologist doesn't concern themselves very much with how to cure you. They're just more interested in finding out what went wrong. Often with dead people, for instance, what is it that caused somebody to die? A person that determines the cause of death is usually a pathologist. So my philosophy is that you can learn a lot about anatomy. You can learn a lot about how the body works by discussing what happens when it breaks down, and what breaks down in order to cause various illnesses and sicknesses. Okay, so let's discuss pathology, and we'll discuss the pathology of different organ systems as we're going through them. Okay, so a couple of terms we need to become familiar with. Symptoms are things that are subjective, subjective signs of a disease. Right, so subjective means that only you can actually, it's something that's unique to you. So pain, for instance, is a symptom because it's very difficult to quantify. It's not objective. It's something that, what you find something that I find very painful, you may not find as painful. Therefore, those are symptoms because it's something that's subjective and unique to the individual. A sign is an objective thing, like a rash or the temperature. If you have a fever, you can actually measure your body temperature with a thermometer. So temperature is a sign. Okay, so illnesses are accompanied by signs and symptoms. The term etiology means an explanation of what went wrong. That's what it is. It's the mechanism of a disease. Right? So if you talk about a disease that is idiopathic, it means you don't know the reason. You don't know the etiology. Right? So idiopathic means you don't know. Right? The term morbidity means sick. Right? So morbidity just means you have an illness or you're affected by a condition, and the word mortality means dead. Right. So, for instance, you may have heard, for instance, that the COVID-19 is a virus, and at the moment we have around 4 million people in the world who are affected with it. So the percentage of the population who are infected with COVID-19 would be the morbidity rate. And then if you take all the people who caught COVID-19 and you ask what percentage of them died from it, that would be the mortality rate. Right? So those are some things from a branch of medicine called epidemiology. And so now we know what symptoms are, what signs are. We know what the etiology of a disease is. If we don't know the etiology, we say it's an idiopathic disease, and then we know the difference between the morbidity and the mortality rate for a particular disease. Okay, so remember those terms. They'll come in handy as we talk about these diseases and illnesses and physical problems later on. All right, so number one, osteoporosis. This is where you've lost more than 50% of your bone mass. It's very common with advancing age. Right? It accelerates in women faster than men, and this is due to menopause, right? And this is where your bones are easily fractured. So that's osteoporosis. We're familiar with that one. What's the etiology? There are many reasons, but the main reason is that as you get older, you have a decline in hormones. Your endocrine system just produces less hormones in general, which causes a lot of changes in your body. But in particular, it causes a decline in calcitonin and some other hormones. All right, Paget's disease is a rapid bone loss in middle age and causes the bones to be easily fractured. And the etiology is that with somebody who has Paget's disease, the osteoblasts are the osteoclasts are overactive. They're too, the osteoblasts are too lazy and inactive. Meanwhile, the osteoclasts are busy tearing apart the bone, and the osteoblasts are too lazy to rebuild it. So the bone is being destroyed faster than it's being replaced. We don't exactly know the reason. So Paget's disease, we know the signs and the symptoms, but it's an idiopathic disease. Right? So Paget's disease and osteoporosis are two diseases of the bone. All right, now let's move on to accidents and the effect of accidents on the bone and breaking bones. The technical term for a broken bone is a fracture. And bone, because it contains osteoblasts, if you break it and you put the ends together, they will actually heal. They will heal together, right? But you have to, but if you don't put the bone back together in the right orientation, it will heal improperly. It'll heal in a funny shape or in a funny direction. So when you break a bone, what they will do is they will reset the bone, right? So you reset the bone into its proper anatomical position, and then you immobilize it with a cast, and you let the osteoblasts in either side of the bone repair the damage and then seal the bone back up again. All right, now when you put the bone back together, when you reset it, if you don't have to open the skin in order to put the bone pieces back together in the right orientation, that is referred to as a closed reduction. On the other hand, if the bone is broken into lots of fragments and you can't really put it back together from the outside of the skin, you have to open up the skin, you have to cut it open surgically and put it back together and then sew the skin back up. That's referred to as an open reduction. Right? Okay, now there's a term here that we're going to come up to in a minute, and the term is called a compound fracture. A compound fracture means that the broken bone has broken out of the skin. There's a common misconception that a compound fracture means that the bone has been broken into many pieces. That's actually a mistake. When you have a bone that's broken into many pieces, you call that a comminuted fracture, and we'll talk about that in a minute. But a compound fracture is where the bone is broken and one of the broken pieces of the bone actually broke out of the skin, so that the bone is exposed. Okay, so difference between an open and a closed reduction, we talked about that, and the difference between a compound and a simple fracture and a compound and something called a comminuted fracture. Okay, so a bone fracture can be open or closed. If it's open, we call it a compound fracture because the bone broke its way out of the skin. A comminuted fracture simply means that the bone is broken in several places, but it could be open or closed. It doesn't say anything about whether the bone fragments broke their way out of the skin or not. Okay, now, if you have a bone fracture, there's several ways that you can describe it. A transverse fracture means that it's straight across, a straight line across the bone, and a transverse fracture can be compound or simple, right? And it can be closed or open, rather. It can be a compound or not. In addition, it can be comminuted or simple, right? So the opposite of a comminuted fracture is a simple fracture. So a simple fracture means there's only one break and then you end up with two pieces, and a comminuted fracture means there are several breaks and you end up with several fractures, right? So generally, you can imagine that generally you have to do an open reduction to repair a comminuted fracture. Okay, so a transverse fracture is a simple straight across break. An oblique fracture is not in a straight line, it's in an oblique line. A spiral fracture usually results from the bone being twisted before it broke. So I'll show you a picture of it, but it basically forms a spiral shape. When the broken bits form a spiral shape. An impacted fracture is where the bone is broken as a result of compression. And then finally, a green stick fracture, a very descriptive term, is where the bone is not completely broken all the way through. It's partly broken, but the break didn't extend all the way to the other side. All right, so here's a simple so here on the left we have a closed fracture. On the right we have a compound fracture that you can see broke out of the skin. And because it's a straight line, this is a simple transverse fracture. Okay, I'm going to show you a picture of a fracture here. If you are squeamish, you might want to close your eyes while I show you this. All right, I'm going to show you a compound fracture that is broken out of the skin. All right, so this is a compound fracture of one of the phalanges, the number one phalange of the finger. We'll talk about that later. However, this is actually fake. This is a fake image. This is a Hollywood makeup job. Well, how do you know? Well, that's because notice that the finger is not flopping around loose. If you broke the finger, if you broke the bone inside the finger, it would just be dangling loose. Here it's not, so the bone must still be there. And somebody just painted another, somebody stuck a plastic artificial bone on top of the actual finger. Right? So this is a fake image, but it looks pretty realistic. Okay, so here we have a comminuted fracture where the bone is broken into several parts. So here we have x-rays showing comminuted fractures. Right? More comminuted fractures. Comminuted fracture of the femur. Comminuted fracture of the distal epiphysis of the femur. Okay, there's a simple transverse fracture. It's not breaking the skin, so it's not a compound fracture. Okay, this is an oblique fracture. It's not a straight line all the way across. It's not a compound fracture either because we can see where the leg is and it's not broken out of the skin. Right, here's a spiral fracture. I have some better pictures of spiral fractures, but you can see it looks like an oblique fracture except that it's kind of it kind of looks spiral shaped when you move the bone fragments apart. All right, this is an impacted fracture. Probably this is the kind of injury you would get if you jumped out of a window on the second floor of a house and you landed on your feet on some concrete below. You would get an impacted fracture like that. That kind of zigzag pattern is typical of an impacted fracture. Okay, a green stick fracture is where the bone is broken on one side only and the break does not extend all the way through. It is named after when if you break a dry stick, a dry twig, it breaks completely. If you break a fresh green twig, a fresh branch, it doesn't go all the way through, right? So you have to twist it in order to break it all the way through. That's the name green stick fracture was inspired by this. All right, I'm going to show you some X-rays, and then you tell me if it's a closed or an open fracture. Is it closed or compound? You may not be able to tell from the X-ray. Is it a simple versus a comminuted fracture? And then can you tell me which bone it is? So you've gone through the handout. You should know some of the names of the bones. Can you tell me which bone it is? All right, so I'll show you this. I'll give you a brief pause, and then you can stop the video if you want, and then I'll tell you the answer. All right, so all of these you've been familiar with before. All right, what would you say about this? In this X-ray, it's fairly obvious. Notice that they've written left, L for left down there. If it wasn't for that, you couldn't really tell whether this X-ray was taken, whether the X-ray was taken through the front or the back, so you wouldn't be able to tell whether it was the left leg or the right leg. That's why the X-ray technician is supposed to write it on there. History is full of examples of the X-ray technician writing the wrong thing there, so that somebody ends up having their left leg cut off and amputated when they should have had their right leg cut off, but the X-ray technician listed the wrong thing. So here it's written. All right, so what bone is that? If you guessed the femur, you're right, and that's just a simple. It's a closed fraction, and it looks like a simple lateral fracture of the femur. Okay, now notice that one of these bones is thin. The one on the left is thin. The one on the lower left is very thin. The one on the right is thicker. And that's a telltale sign that you're looking at the lower leg and not the lower arm. So the lower leg has two bones, the tibia and the fibula, right? And so it looks to me like this is an oblique fracture of the proximal tibia. Okay, here's which bone can you see any recognizable parts? Right, so I would say up there, that's the head of the femur, and so this must be the femur, right? And then it's hard to tell from the X-ray whether it broke through the skin or not, but this could be a compound fracture of the femur. It looks like a simple lateral fracture. Okay, this is the hand. So the bones in the fingers are referred to as phalanges plural, and then individual phalanx, and then we number the if you take these three bones in the finger are each referred to as a phalanx, and then the one that's closest to the body, in keeping with the standard terminology, the one that's closest to the body is called the proximal phalanx. The one that's farthest from the trunk of the body is called the distal phalanx, and then the middle one is called the medial or the middle phalanx. Right? And then we number the phalanxes, we number the digits, the thumb and the fingers, starting with the thumb and calling it number 1, and then this is number 2. Right? So this looks like a transverse fracture of the second proximal phalanx. Is it of the right hand or the left hand? I don't know, because they didn't write it. So it could be either one. Okay, what do you think about this? All right, so that is this the lower leg or the lower arm? Right, so it's the lower leg because you can clearly see that it's the tibia that's broken, and it's a simple transverse fracture of the tibia. Okay, now what do we call, if we call the bones in the fingers the phalanges, the individual phalanx, and you call these bones in the wrist the carpals, what do you call these bones in the middle part of the hand? In the hand, those are the metacarpals. Right? And again, we start from the thumb as number 1. Notice that this is an interesting point. Notice that every other finger is made of three individual phalanxes, right? There's a proximal phalanx, a medial phalanx, and a distal phalanx. The thumb only has 2, right? So the thumb is the only digit. The thumb is the only digit on the hand that has just 2 phalanx is a distal and a proximal phalanx, whereas all of the fingers have a distal, a medial, and a proximal phalanx. So these bones that are in the hand are the metacarpals, and again we number the thumb number 1, and the fact that the thumb has only two phalanxes is an easy way to tell which one of these things is the thumb. Otherwise, it might be a little bit difficult to tell sometimes, depending on the position of the hand or whatever. But because the thumb only has two phalanxes, we can easily see that the thing way over on the left is the thumb. And then we number the thumb 1, and then everything else 2, 3, 4, 5. So that would be a transverse. That would be a simple transverse fracture of the 1, 2, 3, 4th of the 4th metacarpal. I don't know whether it's the right or the left hand because it doesn't say, but actually somebody who's, I believe it's the right hand. All right, are we looking at the lower arm or the lower leg here? Right, so the radius and the ulna are almost the same thickness, and so you saw in the lower leg that the tibia and the fibula are quite different in diameter. The fibula is very thin compared to the tibia. In the radius and the ulna, they're almost the same size, but this looks like a simple non-compound fracture of the radius. Okay, this is kind of nasty. This looks like the ulna broke out through the skin, so that's like a compound fracture of the ulna, and then there's also some fracturing of the radius and the carpals over here. Okay, what about this? So how do you describe the fact that this? So here we have a double fracture, the fibula and the tibia, and the tibia is broken into several parts. So what word do we use to describe that again? So that's a comminuted fracture of the tibia and a simple fracture of the fibula. Okay, this is a beautiful, well, it's awful really, because it's an awful and a terrible thing that somebody had to endure this, but the picture is very clear that this looks to me like a spiral fracture. So it looks like looks like a spiral fracture of, I'm not an expert on bones at all, but I'm not a good enough authority on bones to tell whether that's, I guess that is actually the tibia and the fibula. And so there's a spiral fracture of the tibia, and it's not a compound fracture. Okay, so this is obviously, what is it? How would you describe this? So which bone is it? Yeah, that's obviously the femur. Up here you can see the head of the femur right there, and then you can see the ischium bone, which is part of the pelvis there. Hard to tell whether it's left or right from that without left. Yeah, left. I would have guessed right actually, so I'm surprised. But anyway, then here you see a nice example of a spiral fracture again. So that's a spiral fracture of the proximal femur. Okay, a double fracture. This looks like two green stick fractures of the radius and the ulna. All right, now if you break a bone, it goes through several stages before it's repaired. And if you're what's known as a forensic pathologist, the word forensic means investigating crime scenes and things like that. And so if you have dead bodies, somebody digs up a skeleton and you're trying to identify the skeleton, sometimes you can identify the skeleton based on the fact that certain bones have been broken, and you can see that they've been broken and then healed, right? So if you have somebody's missing and they've been missing for a long time, for years, and then somebody digs up a skeleton and you want to know, is this that person's skeleton? Then you can say, well, I know that person had their tibia broken when they were 8 years old. You can look on the tibia and see if there's a little bump. If there's a little bump, that would indicate that tibia had been broken many years ago and it had healed, but it always leaves a little bit of a distortion. Okay, so when you break a bone or fracture a bone, it is repaired in a very predictable fashion, and it leaves a little tiny bump that can be you can actually look at the bumps and the structures below the bumps to tell how long ago that bone was broken. All right, so when a bone is broken, the first thing you will get is a hematoma. The word hematoma basically means a bag of blood or a bruise, right? So that means that blood flows into the tissue under the skin, but the skin doesn't break, so you get a big swollen bruise that it's red the first day, it turns purple and black the second and third days, and then it disappears eventually. So you start out with a hematoma where the bone was broken, and the blood will clot in about 6 hours. So the hematoma will clot in about 6 hours, and then the blood will be reabsorbed. And then chondrocytes so we have chondrocytes present in the periosteum. So the chondrocytes in the periosteum and the endosteum will begin to build a structure that's called a calli. Will build calli plural, and then callus singular. Right? And the callus is originally made of hyaline cartilage, as you'd expect. Just that's the way bone is formed when we're in the womb, when we're developing, when fetuses and embryos are developing. So the callus will start out being produced by chondrocytes, and it will be made of hyaline cartilage. Eventually, the hyaline cartilage will be replaced by trabecular bone, and eventually by compact bone, but eventually, even no longer how long it's been healed, there'll always be a slight bump that's evidence that that bone was fractured at some point in the past. Now, if you're a forensic pathologist, for instance, and you dig up a skeleton and you see that there's a bone where there's a piece of that bone is made of hyaline cartilage, you know that that bone was broken very recently. If you look at a bone and there's a bump, and you look at that, you saw that bump in half, and you see that it's made of trabecular bone on the inside, you know that it was broken a couple years before or a year before. And then if you saw that bump open, and you see it's made of compact bone, then you know the bone was broken and healed a long time ago. Right, so you can see here we have the original break on the left. The first thing we have is a hematoma, because the blood vessels that are running up and down the Haversian canal have been broken. So that area fills up with blood. Usually, in this case, it's showing that the hematoma is contained by the periosteum. And then the fibroblasts in the chondrocytes inside the periosteum and the endosteum start producing hyaline cartilage, which gives you a callus. Right, so the callus is very weak. The callus is eventually replaced by trabecular bone, right? And then eventually the trabecular bone is replaced by compact bone, but the bone will always have evidence that it was broken and that it was healed. So this is something that forensic pathologists and also forensic anthropologists study. Right, so you know that we have an anthropology department at Columbia. Anthropologists, one of the things they do is they dig up old skeletons, and the anthropologists as well as archaeologists will dig up old skeletons, and then they will think, well, this person lived 8,000 years ago, and obviously they had a very rough life, because we have all these bumps that show that, you know, they broke a bone 20 years before they died, and then they broke another bone 10 years, and they broke another bone 1 year, and they broke another bone just a month or so before they died. So you can see all of these things. By analyzing the state of the skeleton, you can learn something about the person's life whose skeleton that belonged to. All right, so to summarize, we talked about one of the most important things that happens within bones is hematopoiesis. That's the formation of red and white blood cells. We're going to talk about that in detail when we talk about the blood during the cardiovascular unit. Ossification is converting cartilage into bone through mineralization. Basically, we talked about the different types of osteocytes, osteoblasts versus osteoclasts, and how they are involved in bone remodeling. We learned the difference between compact and trabecular bone, spongy bone. We learned about Haversian systems, Haversian canals and Volkmann's canal. We learned about the membranes, the periosteum and the endosteum associated with every bone. We learned about peak bone mass, and we learned about all ways to name all the different structures of a bone. And next time we're going to learn the names of all the important bones in the human skeleton. Right? So thank you very much for listening to this lecture, and I'll see you at part 2.